So there really isn't anything special about the interval between 0 and 1. So this approach for Monte Carlo integration is generalizable to any bounded interval between a and b, where a is greater than negative infinity and b is less than infinity. However, we need to make some slight modifications. So let's consider the more general case, where theta, the thing we want to evaluate, is equal to the integral between a and b of g of x dx. Just like before, let's suppose that x follows the uniform distribution, but this time the uniform distribution between a and b. We know that for a random variable that follows uniform a to b, the PDF f of x is given by 1 divided by b minus a for any x value between a and b. So in this case, theta, which is equal to the integral from a to b of g of x dx, we can multiply it by b minus a outside the integral and multiply it by 1 over b minus a inside the integral. And that becomes the following, the part in the middle. This is equal to b minus a times the integral from a to b of g of x times 1 over b minus a, which is f of x dx. And this part, this integral part, is equal to the expectation of g of x when x follows uniform AB. Therefore, if you want to estimate theta, we can first sample x1 all the way up to xn from uniform AB, get gx bar, which is equal to the sample mean of the gxi's, and then we can calculate theta hat by rescaling the gx bar. And this time we multiply it by b minus a, which is the multiplier in front of e of gx here in the theoretical value of theta. You can notice that in the special case where we want to integrate something from 0 to 1, a is equal to 0 and b is equal to 1. In that case, our x can be drawn from uniform 0, 1, and this multiplier is equal to 1 minus 0, which is 1. So that disappears. Let's see an example for this that involves the normal probability. The standard normal density for a random variable z that follows normal distribution with mean 0 and standard deviation of 1 is given by this f of x over here. I'm not going to read it, you probably have memorized it from a previous class. So suppose that we were interested in finding the probability that the standard normal random variable z lies between negative 1.96 and positive 1.96. This, by definition, is given by the integral from negative 1.96 to positive 1.96 of the normal density times dx. You probably remember that from your first statistics course that the probability that the standard normal random variable lies between negative and positive 1.96 is approximately equal to 0.95. However, let's try to estimate this quantity here using Monte Carlo integration. All right, so to estimate the integral from negative 1.96 to positive 1.96 of this dx, we can first sample x1 all the way up to xn. Here we choose n equals 100,000 from the uniform distribution between negative 1.96 and 1.96, so the lower and the upper bound. Then we can calculate the arithmetic mean of the g of xi's across all of the xi's between 1 and 100,000. We can then take the average. Okay, so after taking the average, we will need to rescale or to multiply it by 1.96 minus negative 1.96. In this case, this is equal to 2 times 1.96, which is 3.92. So let's try to implement the R code for this. First, we specify that n is equal to 100,000. Oh, by the way, the code is complete here in my slides and video. However, for this example, you will need to try to complete the code inside the R Markdown document. So make sure you fill that part in. So we first sample the uniform x's. So we are going to obtain n samples, where this time we sample them from the uniform distribution where the minimum is negative 1.96, so A is negative 1.96, and the maximum B is 1.96. After obtaining the x draws, we apply the g function to each of the x's, and that's given by the normal density. So this is our g function in this case. And that's 1 divided by square root of 2 times pi times the exponent of negative x, our draws squared, divided by 2. Okay, so now we have evaluated the g function at each of the x draws, where x follows the uniform distribution between these two values. Now, we can take the arithmetic mean, the sample mean of the g of xi's, and then rescale it or multiply it by b minus a. And let's call this theta hat. So theta hat is equal to b minus a, 1.96 minus negative 1.96 times the mean of gx. This is our gx bar. And let's see whether the value of theta hat is close to 0.95. Well, this is quite close. So this is nice, meaning that the Monte Carlo estimator for this integral actually results in an estimate that's quite close to the theoretical probability of about 0.95.